So finishing up Unit 4, Worksheet 4. This whole front side, like I said, was all about the law of definite proportions. And I said, I know we talked about a couple different laws, law of definite proportions and law of multiple proportions. And it's easy to get them mixed up. But with law of definite proportions, we're only looking at one compound. Okay, one particular compound, like H2O, something like that. And basically what we're saying is, no matter how much water we have, in this example H2O, we're always going to have the same amount of hydrogen combining with the same amount of oxygen. Really what we're saying is, for a compound, the percentage by mass of each element in the compound will always be the same. So it doesn't matter, like I told you guys in class, we had 1 drop of water, there would still be twice as many hydrogen atoms as oxygen atoms because they combine in a 2-to-1 ratio. Now by mass, that's different though, because the mass of an oxygen atom is actually 16 times greater than the mass of a hydrogen atom. So the ratio of the masses, when you factor in 2 hydrogens and 1 oxygen, for water, it's always going to be 8-to-1 in terms of mass. Can I erase that? So when we go back to number 3, we're trying to figure out if this would be the same exact type of sugar that we had in numbers 1 and 2. And when we did the math for 1 and 2, we found that the percentage of carbon was 42.2%, and the percentage of hydrogen was 6.5%, and the percentage of oxygen was 51.3%. Okay, so we're going to find percentages for carbon, hydrogen, and oxygen in this sugar number 3. So whenever we do percentages, we first of all want to figure out what is the total. Okay, 200 grams. And we say that it's got 80 grams of carbon, 13.3 grams of hydrogen, and 106.7 grams of oxygen. So for carbon, the percentage is going to be 80 grams over the total, which again is 200. And if I divide 80 by 200, I think I get 0.4. Everybody agree? So if I change that to a percentage, I get 40%. Hydrogen is going to be 13.3 grams divided by the total, which is 200, and then that comes out to be 0.0665, I believe, or 6.65%. And then oxygen is going to be 106.7 over the total, 200, and that comes out to be, what was that number? .534 or 53.4%. Okay. So do those percentages all match up nicely with numbers 1 and 2? Why the slight difference? You think it's the same compound? What do you guys say, yes or no? Okay. I would like to, if I'm going to say yes, I would like those percentages to match up perfectly. They're not. So I would go ahead and say no. And so we're really focusing on that point that with the law of definite proportions that we had as our success criteria before, those percentages should always be the same. Because the carbon, the hydrogen, and the oxygen are always going to have to combine in the same way if it's going to be sucrose. Okay? So then on the back side, this is multiple proportions. So on this side, we're not interested in the one compound. We're not interested in the percentages anymore. With the law of multiple proportions, we're going to be comparing different different compounds that contain the same stuff. So like in that last example, that might have contained carbon, hydrogen, and oxygen just like sucrose, but not the same compound because there's different amounts of each thing. If we look at this problem, compound 1 has 15 grams of hydrogen and 120 grams of oxygen. So A says determine the ratio of the mass of oxygen to the mass of hydrogen. Now that's important to see that it says mass of oxygen to hydrogen because that means that when we do the ratio, we should put oxygen on top. Okay? And so for compound 1, the ratio of oxygen to hydrogen is 120 grams of oxygen to 15 grams of hydrogen. And that's my ratio. That's my mass ratio for compound 1. Now we're going to simplify it by dividing. And we'll see that that really works out to be an 8-to-1 ratio in terms of oxygen to hydrogen. Okay? In compound 2, do the same thing. So it says 32 grams of oxygen per 2 grams of hydrogen. So that's going to work out to be a 16-to-1 ratio in terms of oxygen to hydrogen. So these are the two ratios I want to look at. Why aren't they the same? They're not the same compound. Apparently one has more oxygen per hydrogen. What's significant about these mass ratios if I look at them? Anything stand out to you when you look at 8 and 16? Any kind of relationship between 8 and 16? Yeah. 16 is 8 doubled, right? And if we look at these ratios with hydrogen on the bottom being 1 in both of them, really the thing that's doubling is oxygen. So 2 times more oxygen in compound 2. So if compound 1 is water, which is H2O, what could be the formula for compound 2? I'm going to keep the same amount of hydrogen, but I'm going to double the water, double the oxygen. What's that? Right, so if I have 1 oxygen and water, and I know compound 2 has twice as much, H2O2, which we call hydrogen peroxide. Okay? Good with that? So now in 7 we have 3 compounds. Each of them contain just nitrogen and oxygen. Right here it's saying this is the mass of nitrogen that combines with 1 gram of oxygen. So really in A, for compound A, it's saying that it has 1.750 grams of nitrogen per 1 gram of oxygen. B is saying 0.8750 grams of nitrogen per 1 gram of oxygen. So notice the amount of oxygen is not changing. This is important to this law of multiple proportions. C, 0.4375 grams of nitrogen per 1 gram of oxygen. 7A says additional evidence shows that the formula of compound B is NO, meaning 1 nitrogen and 1 oxygen. So now if we're doing law of multiple proportions, we want to compare these different mass ratios. And the first thing I notice is going from B to A is 2 times as big. And again, like we just did on the last problem, the thing that's actually changing is the nitrogen. So if I want to make the ratio twice as much for A, what I'm going to do is say instead of having just that 1 NO, I'm going to say A must have 2 N's. So it would be N2O, and that ratio would work out. I can also see here if I divide these that C goes into B 2 times. But this is tricky. Because if B only has 1 nitrogen, we can't do N 1/2. Can't do that. You got to have a whole number there. So what are we going to do here? Any ideas? Any ideas? Make 2 oxygens. If I make 2 oxygens, really what I'm doing to this ratio right here is just doubling everything. I'm saying the mass of the nitrogen is really like problem B, 8750. But now what I'm doing is doubling the mass of oxygen. Any idea how this ratio right here compares to the ratio in C? They're identical. Okay, so 0.8750 over 2 is the same ratio as 0.4375 over 1. It's just simplified. Okay, so that was a little tricky. It says to sketch particle diagrams. So N2O, I'll make red dot be N, whatever you want to choose. White dot be O. Something like that. Something like that. Something like that. You pretty much justify your representations here with the math. So explain how the examples in question 6 and 7 help to illustrate the law of multiple proportions. These mass ratios change by simple whole number factors or ratios. So going from here to here, twice as big. Here to here, twice as big. Because all we're changing is the amount of one element. So that's always going to be some simple whole number. All right, and that's worksheet 4.